So good morning. I'm Edward, and so I'm going to talk about a new way of evaluating signal function, functional reactive programming. So first, a little bit of introduction. Functional reactive programming is a style of programming where it's functional. Obviously, we have first-class higher order functions, closures, all of that niceness, and it's reactive in that we expect our programs to change how they behave in response to some temporal inputs. So to do that, we make use of two basic abstractions. We have signals, which semantically are functions of time. We do not want to implement them that way, but they are that semantically. And then we have events, which are sort of sequences of temporally ordered occurrences, discrete values. Usually they're labeled with their occurrence time as well, although not necessarily always. The classic formulation of FRP just gives you these abstractions directly, so these are types of values you can manipulate with the combinators. But in signal function FRP, we take that away and we instead give you signal functions, which are transformers of signals and events. One of the main reasons for doing this is it ends up being a little bit more composable. Instead of having values which you've composed, which are built up all the way from a particular sort of input, you can build systems of these transformers that you can then transform or provide different inputs to, as well as transforming the output. So then we get to how we'd like to evaluate this sort of system. Currently, the signal function FRP systems that exist are all evaluated with pull-based evaluation for both signals and events, which says we evaluate when output is needed. And since the system itself is running supposedly in continuous time, this ends up meaning that we just sample the whole system very quickly. So for instance, the current system, the current signal function system, Yampa, samples, has a loop which samples as tightly as possible and will take your CPU. And unless you write some weighting into your input action, there's not really much you can do about that. So push evaluation or data-driven evaluation is evaluating when we have some input available. It'd be very nice to be able to do this for events while still using pull for signals to get as fine a resolution on signals as we can. So this has been done for the classic FRP formulation where you have events and signals as values. This was done by Connell Elliott a couple of years ago, presented at ICFP. But it's not yet been done for signal function FRP for a couple of reasons. So starting out, we generally encode signal functions as an arrow in Haskell. The result of this being that any function we have to lift directly to a signal function. We don't have the option in our abstraction of forcing you to lift it to a particular type of signal function. You have to lift any function directly to a signal function without any annotation on the input or output types. What this means in practice is that we encode combinations of signals and events with pairs, and we encode events just as an option type. So this would be an example of some of the combinators you have. You have the first combinator from arrow, and then capture is a signal function combinator, which will simply, whenever there's an event occurrence on the input on the right, produce a output event which carries the value of the signal at that instant. So another approach to doing this is to use something called signal vectors, which were described by Neil Skolthorpe in his recent PhD thesis. And these describe, in the type system, they describe separate input and output events. And so we have this, this definition in Haskell. If we have the empty data declarations, I would actually like to use data kinds, but when I tried to use it across modules, GHC crashed and gave me several very nasty errors, and so I went back to this approach. So you have an empty signal vector, you have a signal or an event constructor which can carry a type, and then you can append signal vectors together. And this is sort of constructive, so if you append empty and signal, you will get append of empty and signal and not just signal. So we have a couple of examples of what combinators look like in this system. So you can lift a pure function here now to operate just on a single signal, as opposed to your whole input. And then we have first gets reformulated to take the pen type, which is that colon notation. And if you compose these, you get something that operates on the signal on the left and passes through the signal on the right. And the reason I take this approach is because to evaluate signals and events differently, we have to actually be able to represent them separately. So the signal vectors let us distinguish them in the types, and then we can construct different representations of the signal vectors to use in the implementation. Where we can, in a particular representation, we can choose whether we're just going to represent the signal leaves, just represent the event leaves, or both. We can also choose whether from among those leaves we're just going to represent one of the leaves, a subset, or all of them. And we can also apply a type constructor and transform the type of the leaf or not, which is useful for, say, representing the output handlers when you're actually evaluating the signal function. So you can type the set of output handlers with the same signal vector. So onto the implementation, to represent a whole sample, which is all of the signal leaves, we have this type where you can construct a singleton. You have filler constructors for events and signals that don't take any parameters, and then you have the append constructor, which is both down at the bottom. So this representation is guaranteed to contain exactly values for all of the signal leaves in a vector and values for none of the other leaves. We also have a signal delta, which can represent all, none, or some of the signal values, and this is used for during runtime when we are just going to update values within a signal function. We can also represent an event occurrence, and this is an example of the singleton representing a single leaf. We can construct a singleton, and we can say it's on the left or right side and append, but we can't actually represent both sides of the pen. So then to represent signal functions, we actually separate normal signal functions are represented with a single continuation that says, here's your input and your time delta, please produce an output, and a replacement signal function. In this implementation, we have two continuations. One is for time advancement and for event occurrences, but we first have to talk about how to initialize, which is just to provide the initial sample of input, because we're only going to be providing partial samples later on. And so we can initialize a signal function. Once that's done, you have two continuations. This continuation takes, this is a time delta, and a set of some replacement values for the signal leaves, and produces replacement values for the signal leaves at its output, possibly some events, and a replacement signal function for itself, because signal functions have dynamic behavior. And then this continuation takes a single event occurrence, produces perhaps some more event occurrences and a replacement signal function. So that's how events are handled. And this separation is what lets us make events push-based, because during the clock cycles and sampling, we will only work with this first continuation, and we will only be handling the values in the signal parts of the vector. And then as we get events either produced by one of these continuations previously in the network or produced externally, we can handle them with this continuation completely outside and separate from the time steps. So this decouples event occurrence handling from the time steps. So then the way we evaluate these signal functions, the way once you've defined your signal function, you actually plug it into the system and evaluate it. In the EMPA, you're given, like I said, you're given a loop, and you supply input and output actions, and it runs a very tight loop, and these input and output actions must supply the entire new input at each time. And you have to handle the whole output every time, and events, you have to say for each event in your input, yes, there's an event, or no, there's not, every single time. So you have to poll for events. Here we initialize a state with the signal function. We're going to start evaluating initial values for all the signals and handlers for both the signal values and the event values at the output. And then we have a monad, which is just sort of a custom state monad, that carries this and provides an action to push an event occurrence onto one of your event inputs, which will then be handled separately and immediately. And update, which will change the value of a single signal leak on the input, but won't actually cause any immediate reaction. And then there's the set action, which will actually, you supply the time delta, and it will supply all of the previous updates up to the previous step and reevaluate the signal functions. This lets you control the sampling rate more directly and separates out the supplying the event inputs from the signal inputs. So in conclusion, signal vectors let us fix this sort of abstraction leak in FRP where, in FRP we say events and signals are separate, but then we, in the standard error formulation, you have to go right back and make events just sort of a custom signal. Here we actually distinguish events and also allows to distinguish between a composite signal and a set of different signals. This is from Skolthorpe's work as well. And then we show that representing events distinctly from signals in the type permits us to use different evaluation strategies, namely push for events and pull for signals, depending on what sort of thing we're evaluating. What I'm still working on, there's a very nice abstraction in signal function FRP called dynamic collections that I'm trying to bring into this work, which essentially allows you to have a set of signal functions combined into one, but then to add and remove signal functions from this collection. And this is very useful for representing a collection of objects under simulation or something similar that where the size of that collection might change over time. Still working on some demonstration applications so I can do performance comparisons with current signal function FRP. It would be nice to have a semantics and correctness proof. Event merging works differently here than it does in standard signal function FRP, so it would be nice to have a way to argue that this is actually the correct way of handling it. There's also an optimization involving the time independence of signal functions. So not every signal function that you would put in a network is actually dependent on the time updates, and so it would be very nice to actually not even run the time step computation unless there's actual updated input for those that involves, including a little bit more information in the signal functions. So that concludes my talk.
Okay. Questions?
Yes.
So say you're not using the arrow framework, how have you actually implemented this? Is it just as a Haskell library, or have you done your own
Currently it's just a library that exports all of its own combinators. The combinators though correspond to the generalized arrow combinators, which is actually so a pen corresponds to the tuple, the abstract tuple in a generalized arrow, and the empty is there precisely because of the requirement for a unit type in the generalized arrow. But I have not actually written an instance for that yet.
Okay, I'm just wondering because one of the advantages of the arrow framework is the arrow syntax.
Right.
Very easy to construct large networks, which is quite challenging.
And actually at IFL 2011 there was a sort of, it's not quite the same, but there was something that is sort of an abstract syntax. It's a library for writing generalized arrow code as well. So you wouldn't quite, right now you have to sort of program this point free, but there are ways in which you could get around that.
More questions? I have a question. So
yes.
You mentioned this equivalence proof. So how would you approach that? Or didn't you spend much thought about it yet?
I haven't put too much time to it, but essentially the difference is that in standard FRP, if you merge events, you have to say, because events, you know exactly the time of each event occurrence. If you have two event streams and you merge them, well, what do you do if there's two events at exactly the same time? In this formulation, because I've decoupled events from sampling, you know when the last sample was when an event occurred, but you don't actually know the exact time in which it occurred. So I sort of take, I say, okay, I'll take that liberty, and when you merge event occurrences, if there's two occurrences, you just handle them both in a sort of, and the ordering is only defined by which sample time happened last, as opposed to, so you don't actually get, if two events occur within the same sampling interval, you don't actually get to know which order they occur. So it seems like there shouldn't be any problems with that, but it'd be nice to sort of have I haven't actually written down formal semantics for how that works, and then said, my implementation corresponds to that. Yeah.
So what you're saying is that they may not work out to be quite the same, but...
Well, I'm certain they don't work out to be quite the same, but I'd like to argue that it at least makes sense. It's at least consistent.
Okay, thank you again.